A very good day I bid to Dr. Yong and Dr. KJ. My name is Jia Jia.
Hi, my name is Chiu.
Hi, my name is Aizat.
Hi, my name is Syazwan.
Hi, my name is Meyyarasu.
And we are from Group 1. Today, we will be presenting on a plant design project where we convert flue gas into sulfuric acid and methanol. Our presentation today will include an introduction to our problem, followed by the project overview, which is a summary of what we conducted last semester. We will then proceed to the waste treatment strategies that we propose before moving into process economics and cost estimation. So I would like to first pass the floor to Aizat for an introduction to our project.
Thank you, Jia Jia. To begin, allow me to introduce to our problem. Clean Air Regulation 2014 is a regulation where industries need to comply with the new emission limit. The existing thermal oxidizer given in our problem statement consists of SO2 content which exceeds the permissible limit in COR 2014. Therefore, our aim is to reduce SO2 concentration by converting it into value-added products. From a thorough market study that we have conducted, we decided to select sulfuric acid and methanol to be produced from flue gas considering the excellent marketability and value of these two products. With that, let me move into project overview, starting with process screening. This process involves 4 steps where SO2 and CO2 are first recovered from flue gas before being converted into sulfuric acid and methanol respectively. For the recovery of SO2 via regenerable process, Wellman-Watt process has a higher removal efficiency and can achieve higher purity of SO2 gas compared to Cancer process. Hence, this process is chosen for the design of our plant. As for recovery of CO2, ammonia solution is chosen against amine solution as ammonia requires lower regeneration energy and is not degraded by SO2 and O2. Once we have recovered the required gases from flue gas, we proceed with the conversion of these gases into value-added product. Wet gas sulfuric acid process is chosen to convert SO2 to sulfuric acid due to its simple plant design and high steam production, which can be used as heating utility for the plant. The route chosen to produce methanol from CO2 is dry methane reforming, which has higher yield of methanol production using cheaper raw materials. From the process screening conducted, we can construct the process flow diagram for the plant, which will be presented by my colleague Syazwan.
Thank you, Aizat. Let me give a brief overview on our process flow diagram. As shown in the block diagram, this process starts with flue gas entering the plant from the existing thermal oxidizer, where it is cooled and directed to an SO2 absorber. This absorber is a part of the Wellman-Watt SO2 recovery unit, which recovers SO2 from flue gas using Na2SO3 as the adsorbent. The SO2-rich gas from the adsorber then undergoes the wet gas sulfuric acid process to be converted into 99.8% of sulfuric acid. The dissolved gas, on the other hand, is sent to the CO2 recovery unit, where cold ammonia scrubs CO2 off the flue gas. The recovered CO2 then undergoes dry methane reforming to produce 99.7% methanol as the distillate product. This is the process flow diagram for our plant, consisting of the Wellman-Watt process, wet gas sulfuric acid process, cold ammonia scrubbing, and dry methane reforming to methanol. We then conduct heat integration design through pinch analysis, where we managed to reduce the utility by 81% through an addition of 5 heat exchangers. The process flow diagram after heat integration is shown here, where the heat exchangers are indicated in red colors. The separation system in our plants includes an SO2 absorber to concentrate SO2 gas, a CO2 absorber to concentrate CO2 gas, and a distillation column to separate methanol from methanol water mixture. On the other hand, the reactors are dry methane reforming reactor, SO2 to SO3 oxidation reactor, and methanol synthesis reactor. This equipment will be designed by each of my colleagues and will be presented in their respective presentations. Now, let us move on to the control strategies implemented in this plant, which will be presented by Mia. Thank you.
Thank you, Syazwan. Now let's have a look on control strategies. The 4 main types of control strategy used here is feed-forward control, feedback control, cascade control, and ratio control. We implement this control strategy on all equipment in the plant such as the methanol distillation column, SO2 absorber, and DMR reactor, and represented the control strategy in the form of piping and instrumentation diagram as shown here. Now let's move on to asset and operability analysis. HAZOP is used to examine and inspect each operation unit in the design plant in order to determine all possible hazards that may arise in the plant. One example of HAZOP study for methanol distillation column is shown here, where we study on different parameters such as flow, temperature, pressure, and level. The other equipment are studied accordingly based on the same parameters. Now let's have a look on plant layout. Our plant is divided into process and non-process area. Process area is located at the east side of the plant since the wind direction is toward north and northeastern Kerteh. This is done to ensure the employee receive minimal negative impact from plant emission. Each solid location for product and raw material is accessible by road for easy transportation. As a safety precaution, the fire and emergency brigade as well as HSE building are located close to both process and non-process area. The plant layout is designed such that utmost importance is given to safety of the employee. With that, we completed the project overview that we conducted last semester. Now, I would like to pass the floor to Chiu.
Thank you, Mia. I would like to move on to the waste treatment strategies. Waste can be generally categorized into solid, liquid, and gas phases. In our plant, all three phases of waste are generated. Gaseous waste come mainly from the flue gas, liquid waste come mainly from the effluent of separators, while solid waste come in the form of catalyst and sludge, which are classified as scheduled waste. For gaseous waste, the first limit that our plant should comply is the Environmental Quality Clean Air Regulation 2014, which serves to regulate the release of air pollutants from the industrial activities. Since this plant is a waste treatment plant which converts flue gas into value-added product, Section K for waste incinerators should be followed. The three components that we should comply are SO2, NO2, and CO, with their respective limits. Apart from waste gas emission, effluent and scheduled waste generated should adhere the Environmental Quality Industrial Effluent Regulation 2009, which applies to any premises that discharge effluent into inland Malaysia. Since our plant is not located in any catchment areas listed in the 6th schedule, so it follows Standard B. As come to solid waste, all solid waste in our plant are classified as scheduled waste. Scheduled waste are waste which leads to explosion and fire when mixed with other substances. The Environmental Quality Scheduled Waste Regulation 2005 classifies the scheduled waste into several categories, where the catalyst from this plant constitutes largely of SW1 due to the presence of metal content. Since this plant is essentially a waste gas treatment plant, all gas emissions of the plant are designed to adhere by the regulation limits where SO2 concentration is reduced to 17.94 mg per meter cube, achieving the CAR 14 limit. Hence, our design objective is accomplished. With gas emission achieving the required standards, we will be focusing on the wastewater treatment strategy. This treatment process is categorized into preliminary, primary, secondary, and tertiary, as well as solid waste treatment. These are the equipment used for wastewater treatment strategy. The EPAS separator, which works on the basis of Stokes' law, separates the suspended solids and oil from the wastewater based on gravitational pull. The effluent of APS separator flows into an equalization basin where its flow rate and pH are regulated by the addition of an acid or a base to maintain constant feed quality to the chemical treatment system. In the coagulation tank, the chemical dosing will be added to cause smaller particles to accumulate into larger sized particles that are effectively removed through sedimentation. The effluent of coagulation and flocculation tank would then send to DAF unit. By using air bubbles, particles with lower densities compared to the liquid can be easily skimmed out as they float to the surface. The wastewater would then proceed to secondary treatment where aeration tanks are used to promote the growth of microorganisms. These microbes feed on organic matters such as urea and phosphate to form larger flocks which easily settle out of the wastewater. All flocks collected are channeled to the clarifier and sediment as sludge. Gross solids and suspended solids present in the refined effluent can be separated with basic media filtration, which remove remaining tiny particles size approximately 5 micrometers. The wet sludge would then send to the sludge thickener unit for removal of moisture, where sludge solids settle via gravitational pull. The wet sludge from the sludge thickener would then further treated in a centrifuge. All scheduled waste are sent to Quality Alam Sdn Bhd for designated waste treatment processes. With these strategies, we can ensure that all effluent and emission by the plant abide by the regulation limits. Next, I will then pass the floor to Jia Jia to describe on our next part of design process. Thank you.
Thank you, Javin. I would like to now move on to process economics and cost estimation of our plant. CAPEX, also known as total capital investment, refers to the amount of expenditure required for the building of the plant, comprising of the fixed capital investment as well as the working capital. FCI deals with the costs involved in constructing and equipping the plant with process equipment and facilities, which involves manufacturing and non-manufacturing costs. Working capital, on the other hand, involves the necessary expenses for general operation of the plant. All major and minor equipment in the plant will be estimated for its purchased cost using these two equations. Since these equations are based on year 2004 as well as year 2000, the cost index method can be utilized in order to obtain the current cost. From these equations, the total PCE is around 113 million ringgit. From the PCE, the physical plant cost as well as the indirect cost can be calculated using appropriate factors called the Lang factor. From there, our fixed capital investment is 561 million ringgit. Next, the working capital, which includes inventories costs, are calculated as 15% from the fixed capital investment. Summing both working capital and fixed capital investment, we obtain the capex as 646 million ringgit. The operating expenditure of a plant is contributed by direct operating costs, namely fixed and variable operating costs, as well as the indirect operating costs, which includes general expenses of the plant. All aspects of fixed operating costs are calculated, amounting to 172 million ringgit per year. Variable operating costs depends on the level of production, which includes raw material costs, utility costs, and miscellaneous operating costs. Indirect operating costs involves general expenses of the plant, such as administrative costs, distributing costs, and R&D costs. From this, the calculated OPEX is 742 million ringgit per year. The total gross income generated by the plant is 321 million ringgit per year. Economic potential analysis is conducted to evaluate the preliminary profitability of the plant, where we achieve an EP3 of 579 million ringgit per year, showing good economic feasibility. The next step is project economic evaluation. Large-scale plants require techniques which include the rate of return, payback period, net present value, as well as discounted cash flow rate of return. All calculations for economic evaluation will be made using the following assumptions, where the plant has a plant life of 15 years, with yearly operation of 330 days and daily operation of 24 hours. The MARR is fixed at 20% and the yearly income tax is 25% of net profit. By evaluating the cost for startup period, which is 3 years before commissioning the plant, as well as depreciation costs, we can obtain the rate of return of the plant. Rate of return refers to the total gain or loss on the investment over the project lifetime. Our plant has an ROR of 26%, which is greater than the MARR of 20%, hence it is economically feasible. Payback period refers to the time required for the investment to break even and generate net profit. The payback period for our plant is 5 years, which is appropriate for a 15-year plant. Next, we can evaluate the net present value, which is the difference between cash inflows and cash outflows discounted to the present time. Since the NPV is a positive value, this project is economically feasible. DCFRR is calculated through a trial and error approach until the discounted cumulative cash flow at year 15 amounts to 0. The DCFRR obtained is 35%, which is greater than the MARR of 20%. Hence, this project is feasible even after accounting for the depreciation effect. Based on the calculations performed, this plant has a capex of 646 million ringgit as well as an OPEX of 743 million ringgit per year. With an EP3 of 579 million ringgit per year, both ROR and DCFRR of the plant is well above the MARR of 20% with a payback period of 5 years out of a total of 15 years. In conclusion, this plant is designed to produce 41 kilotons per year of sulfuric acid, as well as 546 kilotons per year of methanol. All plant emissions comply by CAR 2014, including SO2, in which concentrations is reduced to 17.94 milligrams per meter cube. The utility saved from heat integration achieves 81% of the total heating and cooling duty. Waste treatment strategies are also proposed to ensure that all emissions and effluents from the plant abide by government regulation limits. Profitability analysis show that this plant is economically feasible. Future work will involve the detailed study on the health impacts of the plant, considering that this report only focuses on environmental concerns. Further improvement of the plant for the reduction of cost can also be performed to retrofit the heat exchanger network. And with that, I would like to end our presentation today. Thank you.